question that this is answering is, say that you're given the stress tensor in one coordinate system. What would the stress tensor be in another coordinate system? That's all we're trying to do. Okay. And this is based on a rotation matrix. And rotation matrices are really useful things in all sorts of branches of physics and engineering. And so here's the idea. So let's say that we have this, so here's our coordinate system. And in this coordinate system, we have a vector where this angle is 30 degrees and the magnitude is 10. Okay. And so in this coordinate system, that vector, the components are 10 times cosine of 30, 10 times sine of 30, and so that's 8.665. But you can represent this vector in any coordinate system. So in a different coordinate system, components of the same vector would be different. So now let's say that we're going to use a coordinate system where the x-axis is this, okay? And this x-axis makes an angle of 30 degrees with the horizontal. Okay. Then now we'll take our original vector and put it in this coordinate system, and you can see that it would just line up perfectly with the positive x-axis. This has a magnitude of 10. Well, the components here, it just goes straight 10 along the x-axis. There's no component in the y direction or anything. And so the components here are, 10, 0. And so the idea of a rotation matrix, I mean, this we just did by sort of reasoning it out. But a rotation matrix and I'm going to always call it Q, and I can't remember what Q stands for, but it's a matrix Q. Is a matrix that you multiply to the components of a vector in one coordinate system and after you multiply it, it gives the components of that same vector in a different coordinate system. So I'm going to give you the general rule for coming up with a coordinate system now. This is probably not the one that you're going to use in practice, but so let's say that you have a coordinate system A and a coordinate system B, okay, where the axes have different orientations. Then a rotation matrix Q that takes vectors from coordinate system A to coordinate system B has columns, like the matrix columns, that are the coordinate system axes of A expressed in the coordinate system B. Okay, so, I mean, I always remember this as like if you're going from coordinate system A to B, then the columns of the matrix are the axes of A in B, you know, it's A, B, A, B. All right, so let's see how this works on this example. So our coordinate system A is this. And the z-axis coming out. And our coordinate system B is this. And z is still coming out, so z isn't going to change. So this is B. So what we want, since we start out with a vector that's expressed in this coordinate system, and we want a vector expressed in this coordinate system, or that's what I did in the example. So we want the axes of this coordinate system expressed in this coordinate system, and that'll give us the columns. Okay, so if you have, so the first axis is the x-axis, okay? So take the x-axis and express it in this coordinate system. So if I took the tail of this vector and put it here, what would be the components of that vector in the B coordinate system? Well, you could think of it as so if you put this vector here, to get from the positive x-axis to that vector, it would be negative 30. So it's going to be cosine and sine of negative 30, and then 0 for z. So cosine and sine of negative 30 is 0.866. And now these are the columns, so negative 0.50. So this is the x-axis of A expressed in B. Okay. And now take the y-axis of A and express it in this coordinate system. That's going to be positive 60. So positive 0.5, positive 0.866, 0. So that's the y-axis with all the other. So you'd have to, so you put this vector over here, and then you'd have to figure out the counterclockwise angle from the x-axis to that vector. In this case, it would be 60, and then cosine and sine of 60. And then the third one is take the z-axis in this coordinate system. What would be the components of the z-axis if you expressed it in this coordinate system? 0, 0, 1. Yep, great idea. Okay, so now we're going to multiply this matrix times, so 0.866, negative 0.5, 0, 0.5, 0.866, 0, 0, 0, 1. And we're going to multiply it by the components of the vector in the A coordinate system. So that was positive 0.866, nope, at a length of 10. So this is 8.66, 0.5, nope, 5, 0. Okay. And you get 7.5 plus 2.5 for the first component. Negative 4.33 plus 4.33 for the y component. And 0 for the z component. 10, 0, 0. Okay. That was, so what we were doing is what we did in this example. So we first started out knowing the components of this vector in this coordinate system. And 8.65, oh, I guess let's make it all 3 dimensions. So 0, this is a 0, this is a 0. So we started with this. We made a rotation matrix that goes from this coordinate system to the next one. And then we multiplied this to the rotation matrix. And what we got was what we had already figured out should be the components of that vector in this rotated coordinate system. Yep. In practice, that's not the way we're going to think about it. We'll think about it in an easier way. So this is an easier way to think about rotation matrices. Okay, so first, if you are rotating, so 1, to rotate the original coordinate system, an angle theta about the x-axis. Your rotation matrix is 1, 0, 0, 0 cosine theta, sine theta, 0 negative sine theta, cosine theta. Second, to rotate the original coordinate system theta about the y-axis. Q is equal to cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cosine theta. And then third, to rotate the original coordinate system theta about the z-axis. The rotation matrix is cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. Okay, so you could come up with any crazy three-dimensional rotation as a combination of these things. In this class, you won't ever have to do more than one of those rotations at a time. But there are two things I want you to notice about these. The first thing is there's a pattern, but remember that the y-axis always has to be the weird one. Okay, so like with the cross product, when you get to the y component, there's a negative sign that the other two don't have. When you're taking the cross product of coordinate system axes, x cross y is equal to z, y cross z is equal to x, but x cross z is equal to negative y. Just y is always trying to be a little bit of a pain in the butt. And you see it here too. So look at this pattern. So in every case, you have ones and zeros for the row and column connected to, you know, the component that you care about, the axis that you care about, the 1, 0, 0, 0, 0. And then you have cosine, sine, negative sine, cosine. You have that for x, and you have that for z, but y has the negative switched on the sign. Okay? It's just got to get its little thing in, you know. It's like it's mounting just a little too much attention to it as a kid. Your special y-axis. And then the second thing is the inverse of any rotation matrix is the transpose. And that's nice because inverses are a pain to do, especially by hand. I mean, the calculator will do it basically instantly, but if you're doing it by hand, an inverse is a real pain to do for a 3 by 3 vector, but a transpose is easy to do by hand. Okay. And that's nice because if you're going from coordinate system A to coordinate system B, and the rotation matrix is Q, then to go the other direction, so say you start at coordinate system B and you want to go back to coordinate system A, the rotation matrix there is Q transpose. Any questions yet about this? So let me do an example that is something you'll recognize from Physics 1, but sort of a new way to think about it. So let's say we have this incline. And let's say this angle is 20 degrees and you have a block on this incline. Okay. And when you do this in Physics 1, the coordinate system you choose has the y-axis going out of the surface and the x-axis along the surface. Okay. Say this has a mass m. So what's the weight force vector in the coordinate system shown? Well, you know, you're used to doing this with trigonometry. You draw a triangle or whatever, come up with the components. But you can also do it because in this coordinate system, the weight force is, you know, easy, instant to figure out. 0, negative mg, 0. And then if we want to go, so to start with this, we already know this. Okay. So we want a rotation matrix that takes this coordinate system to this one. So to go from here to here, you need a theta of positive 20 degrees about the z-axis. Whether it's positive or negative comes from the right-hand rule. Okay, so this, since we're rotating this way, that's a positive z angle. And so the rotation matrix is cosine of 20, sine of 20, 0, negative sine of 20, cosine of 20, 0, 0, 0, 1. Okay. And so in the new, so in the rotated coordinate system, that weight force is cosine of 20, sine of 20, 0, negative sine of 20, cosine of 20, 0, 0, 0, 1, times our original vector, 0, negative mg, 0. You get negative mg sine 20, negative mg cosine 20, 0, which is what you would have gotten, thinking it through in terms of triangle legs and stuff. I mean, I did it like, I did this in a very, really exaggerated steps. But if you have this programmed in your calculator, and so it looks like way longer to do it, like why would you do it the hard way when you're already so used to doing it the other way? But there are a million cases, and this is one where if you have this programmed in your calculator and you're used to thinking about things this way, then you just like punch it in, gives you the answer, and it's quicker to do it this way than to have to try to think through the components. Anybody have any questions about that? Okay. Well, so this was all for vectors. So this was all for expressing vectors in a new coordinate system. But now we're going to do it for tensors. So if Q is a rotation matrix, that goes from an old coordinate system to a new coordinate system, then the stress tensor expressed in the new coordinate system is equal to Q times the stress tensor in the old coordinate system times Q transpose. So one thing to notice about this, y for vectors, you only need to multiply by one rotation matrix, and here you have to multiply by 2. So you need 2 rotation matrices for tensors. One changes the orientation of the stress cube, or the axes means the same thing. And then the other one expresses the tractions on the cube faces in the new coordinate system. Okay, so think of, a stress tensor is a stress cube. They're equivalent to each other. So imagine a stress cube with all these different traction values all over the face, okay? Well, you have to do two things. You have to multiply by a rotation matrix in order to change the faces, okay? So that now we're talking about tractions on different faces, okay? And then we have to take those tractions and re-express them in a new coordinate system. That's where the two come from. That's not something you really, really like have to have in mind, but if you're ever curious about it, that's what the two are doing. Okay, so let's say that we have a stress tensor that's represented by this cube. Let's say that this is 6, this is 10, let's say this is 8, this is 5, and 2. Okay, so let's say that that's our stress, that represents our stress tensor, okay? And we'll start out with it in this coordinate system, okay? And then we'll figure out what's the stress tensor in. So for this one, let's go YZ. Let's change it to x-axis that way, y-axis that way, z-axis back. Okay. Well, in this coordinate system, XX is 6, YY is 5, ZZ is -8. And then we have 0XY. We have +10XZ. And then YZ, we have +2, so +2. Okay. So how would you get from this coordinate system to this one? We need a rotation matrix. What are we doing? You could think of it as two different transformations. In order, we're going, so you could rotate 90 degrees about the z-axis. So +90 about z. And we're not there yet, because then we have x pointing up, but y pointing this way and z pointing this way. So after you do that, you have to rotate 180 degrees about the x-axis, about the new x-axis. You see that? We could use plus or minus, but let's say +180 about x. So then Q is going to be, like when you multiply these, you multiply from the right side to the left side. So our first one on the right side is going to be, so cosine of 90 is 0. We're doing it about z. Sine of 90 is 1, then 0, then negative sine of 90, then 0, okay? And then we're going to multiply that by a 180-degree rotation about the x-axis. So cosine of 180 is negative 1. Sine of 180 is 0. Negative sine of 180 is 0. Cosine of 180 is negative 1. Now we'll multiply these two together. You get 0, 1, 0. One, 0, 0, 0, 0, negative 1. Okay, so that's our rotation matrix. And remember, we can also do these just using the definitions of, so these have to be the axes of our starting coordinate system expressed in our new coordinate system. So the x-axis in our new coordinate system would be 0, 0, 1. It's just straight along the y-axis. The y-axis, not the z-axis. So 0, 1, 0, and that's what we got. Remember the definition that I said at the beginning, like the columns of the rotation matrix are the axes of coordinate system A expressed in coordinate system B. So, so if we take the x-axis of coordinate system A and express it in here, that's going to be 0, 1, 0. And that should be our first column of our rotation matrix, and it was. Then the y-axis of coordinate system A is along the positive x-axis of that, so that should be 1, 0, 0, the second column, and that's what it is. And then the z-axis, put that over here, it's in the negative z direction, so it should be 0, 0, negative 1, and that's what it was. So this is our rotation matrix. And now we're going to say this new coordinate system is 0, 1, 0, 1, 0, 0, 0, 0, negative 1, times our original coordinate system, 6, 0, 10, 0, 5, 2, 10, 2, negative 8, and then times the transpose of that rotation matrix. So what was the first row is now the first column. What was the second row is now the second column. Oh, it's the same. 0, 0, negative 1. It doesn't have to be the same, but it is in this case. Okay, so now what order do we have to multiply these? Doesn't matter, that's right. We could do this times this, and then multiply what we get to this, or we could do these two together and then multiply times this. So 0, 1, 0, 1, 0, 0, 0, 0, negative 1 times, so I'll do these first. You get 0, 6, negative 10. Uh, 5, 0, negative 2. 2, 10, positive 8. And then multiply these out, and you get 5, 0, negative 2, 0, 6, 10, 2. Ooh, something went wrong there. Yeah, this has to be symmetric because this is our stress tensor now in the new coordinate system. Oh, does it come out to be negative 10? Which one? This should be negative. Yes, negative 10. But either that 2 should be 0. Here? Okay. And then negative 10, and then negative 8. Okay. Can we make any sense out of whether this is right or not? In this example, we can, because this cube in this coordinate system, all the faces are still aligned. They just have different names. Okay. So in this coordinate system, this would be our x face. Okay. And the traction on our x face would be 5 in the positive x, 0 in the y, and negative 2 in the z. So it should be so 5, 0, negative 2. Oh my God, it worked. Yes.
Do we even need to figure out the angles that it rotates if we just know the final coordinate system?
Well, I mean, in most problems, yes, you do. In this problem, there's 2 ways to do it. But I'm doing that so we can sort of check our work and kind of try to make sense out of this, make all these ideas sort of come together. Okay, and then the second one. So now the y face is this once we rotate the coordinate system. So we should have 0 for x, positive 6 for y, negative 10 for z. So 0, 6, negative 10. That one works too. It's all going to work. You did help me, though. And then z, this time, the Z face is that face in the back that we don't usually think about, you know. But what we do know is that the tractions on the back are equal and opposite to the tractions on the front. So on the back, we have a x component in the negative x direction of 2. So negative 2. And then we have in the y direction, it would be the opposite direction. So it would be negative 6. And then in the z direction, where, oh, yeah, negative 10. I meant this one has a magnitude of 10. What did I say for x? We have negative 2, negative 10, and then an 8 in the positive z direction. So negative 2, negative 10, 8. Come on. Oh, yeah, because I didn't switch the direction. Yeah, so on the other face, it would be this way, which is negative 8. So, right, negative 2, negative 10, negative 8. Yeah. I could not have gotten through that without you. Well, this rotation, this transformation thing, it may not be super clear why it would be useful to, like, why you really care about what coordinate system you use. But we're going to see that this is an important idea for figuring out the principal stresses, which is where all you have is normal stresses. And that ends up being an important thing for figuring out where failure is going to happen in a material. So this actually is a really useful idea.